So this will be the first of 4 lectures on special topics this week. Here it is. The first 2 lectures will be on quantitative aspects of unification. And then the second 2 lectures will be quantum search algorithms. Some of you may have heard already the lecture about Koopman von Neumann, formulation of classical mechanics leading to formulation of mixed classical quantum theories of a new kind. That was an open-ended lecture. And similarly, the quantum search algorithms will be somewhat open-ended. This first pair of lectures on quantitative aspects of unification will be mostly an exposition of material that's been around for a long time, but it's becoming, it's already classic. I think it's very important material about how we might unify the different forces. And also it's very topical. A different title for this series will be, might have been, Why I Will Be Disappointed if supersymmetry is not discovered at the LHC. So I'm going to try to convince you that you all should be rooting for supersymmetry to be discovered at the LHC, that it would improve our understanding of the world, and seems to be a very logical and compelling implication of things we know if we follow out their logic. So there'll be some interesting mathematical issues along the way having to do with spinors, group theory, different kinds of fermions. I hope that will also have some interest for people who are primarily interested in condensed matter physics, where different kinds of exotic fermions have become a major topic in recent years. So ever since it was clearly formulated by the early 1970s, the standard model based on gauge theories of SU3 for the strong interactions and SU2 cross U1 for the electroweak interactions, broken at low energies to U1 of electromagnetism, has gone from success to success. It would be difficult to exaggerate how accurate and comprehensive this has turned out to be. Especially if you combine it, as you can very smoothly, and basically uniquely with general relativity, to give a theory we can use in astrophysics and all kinds of phenomena where both gravity and the other interactions are important. There's a lot of discussion of the fact that quantizing gravity is a very challenging problem, and that's true. However, the problems that arise in the theory that you get by just combining these two ideas in a straightforward way don't really arise until you examine curvatures much, much larger, or events that happen much, much more rapidly than any that appear to occur in the natural world, certainly in laboratory environments recently. You have to go to the interior of black holes or the origin of the universe to find places where the equations you get from this structure break down. So this is close to nature's last word. It gives us an extraordinarily accurate and precise account of all of chemistry and most of physics, as Dirac said back in the 1930s. But that was, in those days, the understanding was relatively primitive. Now we have a much more precise realization of his vision that the fundamental laws governing matter under enormously wide variety of circumstances are known and have been tested in far more extreme conditions and far more accurately than we need for practical applications in all kinds of fields ranging from chemistry to biology to nuclear astrophysics. So we should take the remaining flaws or the apparent aesthetic shortcomings of this structure very seriously, because it's close to nature's last word. We're not going to get anytime soon, unless something unforeseen happens, a great deal of experimental information about phenomena that are outside of this structure. So what are the aesthetic flaws of this very successful and remarkably economical structure? Well, one is that we have 3 or 4 forces that are apparently loosely connected or independent. So we'd like to have one in a unified theory. If we look beyond the symmetry to the structure of matter, that is the fermions, we find that although they come in multiplets, so all the different fermions that are thought to be fundamental are not independent, nevertheless they fall into several independent groups. In fact, as you'll see, 6 independent groups, or I should say, not to confuse things, let's say not groups but multiplets. And then on top of that, there are 3 repetitions, the 3 families. There's electron, muon, and tauon leptons. And similarly, all the quarks and neutrinos all get replicated 3 times over. There's also, if you examine the structure of the theory, as we'll discuss, funny numbers, funny pure numbers, which are the hypercharge assignments. Of our fundamental fermions. So this U1 looks very, very the way it's implemented in the theory looks very, very peculiar and lopsided as it acts on the fermions. And then finally, there's a whole mess of masses and mixings, things like the Cabibbo angle, the different quark masses, that at the present level of understanding are just put in as phenomenological parameters. So I'm going to be describing to you ideas that come close to solving these three problems. Certainly address them in a profound way. Profoundly. They won't solve all problems because we'll still be left with this, but they will address those flaws. I should say there's also another flaw which is not aesthetic but phenomenological, which is that the standard model as it stands has no explanation of the dark matter that astronomers want. And we'll have a hint about this, but it's not as compelling as the ideas that address these first three problems. Okay, as you'll see, the ideas that address these problems have quantitative power as well as being pretty, and lead to definite predictions which might be right or might be wrong, and that's part of what makes them exciting as well as nerve-wracking. We don't know yet what the fate of these ideas is going to be. So the basic thought that leads to the idea of unification is that the standard model, or at least three of the four forces in an obvious way, are based on different kinds of symmetry, gauge or local symmetry. So they all have the same mathematical structure. Basically, they are generalizations of Maxwell theory of electromagnetism, just with more kinds of charges, colored charges of SU2 or SU3, leading to so-called Yang-Mills theories. And this structure is just begging you to consider the possibility that the three forces of nature that we see as independent at low energies derive from a larger force, a larger symmetry of the same kind, such as SU5, or we'll see a beautiful kind of unification can be achieved with SO10, the group of rotations that preserve Euclidean metric in a 10-dimensional space. Now, it's certainly easy at the level of group theory, as we'll review shortly, to incorporate these symmetries very neatly and compactly into either of these structures. And furthermore, we know now very securely and in detail how symmetries can be broken. In the case of the electroweak theory, we had SU2 cross U1, weak isospin and hypercharge, breaking down to electromagnetism. This is a theory for which several people have won Nobel Prizes, most recently Higgs and Engler, for describing how the symmetry can be broken with the Higgs mechanism leading to the successful prediction of a Higgs particle. And this is a model, that is a model, I should say, for how a larger symmetry can be broken down when you have condensates filling the world into a smaller symmetry. So if the symmetry of the equations is smaller than the symmetry of their stable solutions, if you have condensates that are not invariant under the full symmetry of the equations, you have this structure of symmetry breaking, and that's something that was startling back in the 1960s, before my time, but has now become second nature to physicists, the idea of spontaneous symmetry breaking, and including spontaneous symmetry breaking of gauge symmetries. Okay. So that thought is very easy, but what's very non-trivial, what's not trivial at all, is that the fermions, the quarks and leptons, can be organized well, let me pose this as a question, actually. Can the fermions be organized into reasonable multiplets of the larger symmetry? Do the different pieces that transform in particular ways under SU3 cross SU2 cross U1, do those pieces fit together into something that transforms in a reasonable way under SU5 or SO10? Okay. And so the first part, the first substantial part of this lecture, now after the introduction, will be discussing exactly that issue. So to do that, well, first let me take questions. Is there?
Just one
Yes.
So you mentioned the fermions comes with 6 multiplets in the standard model.
Yes.
The 6 comes from 3 plus 2 plus 1?
No, not at all. The 6 comes from what I'm going to show you right now. The 6 comes from the observed properties of particles. It's a phenomenological number that, at the present level of understanding. Okay. So now I will write down, without further ado, the multiplet structure of the Standard Model. There are 6 entities. The most complicated of which is the left-handed quark doublet. So I'll write down and then I'll explain the notation. Okay. First of all, left-handed refers to the fact that we should formulate the theory at first in terms of massless particles, which can have either left or right-handed helicity. So these are Weil fermions that are left-handed in this case. The great discovery of parity violation in the weak interactions indicates that left-handed and right-handed particles have very different weak interactions, even if they have otherwise the same properties. For purposes of this lecture, so as not to get bogged down in too much detail, I'm going to make two simplifications. First, I'm going to pretend all the fermions are massless. And secondly, I'm going to pretend only one family. So I will write down the electron, but not the muon and the tau lepton. I will write down the U and the D quarks, but not charm, strange, top or bottom, and I will only write down one kind of neutrino. These are inessential simplifications, but they do make life easier, and I don't want to obscure the main point by getting bogged down in those kinds of details. Okay, so here SU3 acts horizontally. That's the strong interaction. So these are red, white, and blue. Or let's be less xenophobic and call it red, green, and blue. Color charges of the strong interaction. And the SU2 acts horizontally. So these are doublets under the weak isospin. So the left-handed quarks do have weak interactions. And form a doublet. And this 1/6 is the hypercharge, which is the average charge average electric charge. And that measures the strength of the U1 coupling. Okay. And if you write down this structure for the quarks, that's all you need to know to predict their properties under the strong electromagnetic and weak interactions. Nothing is hidden. That's all there is. This tells how precisely it couples to all the colored gluons, to the W and Z bosons, and to the photon. So a lot of physics is encoded here. And then the other things that we have are right-handed up quarks, which I'll write like this. They do not have weak interactions. They are singlets. And the average charge, but they do have, of course, color charges. They're strong interactions. And their average charge is the charge of the up quark is 2/3. Similarly, we have the right-handed D quark. And then we have the left-handed lepton doublet. So no color charges this time, but we do have a doublet under the weak interactions, and the average charge is -1/2. the hypercharge. And then we have the right-handed electron, which does not participate in the weak interactions nor the strong interactions, but does have electric charge, so it's minus 1/2. So those are 5 different entities out of the 6 that I mentioned. The 6th is a funny one, which you might call the right-handed neutrino. It has no electromagnetic interactions, no strong interaction. It's a singlet under SU3. It has no weak interaction. It's a singlet under SU2. And unlike the right-handed electron, it also has no hypercharge or ultimately electromagnetic interaction, and so it gets a 0. So it's completely inert as far as the strong electromagnetic and weak interactions are concerned. Nevertheless, so it's not an easy particle to observe. However, there is indirect evidence for this from the fact that neutrinos have non-zero mass. I won't pause to explain that theory at this point. If there's time, I'll go back and discuss the theory of neutrino masses and why it's very desirable to have this extra particle. I should mention that the most recent Nobel Prize in particle physics was for the discovery of small neutrino masses, which might seem like a really esoteric and unimportant curiosity. However, it's enormously important in the context of unification and really justifies the existence of for us thinking that there should be this kind of particle, and really was a triumph of unification historically because it was small neutrino masses were predicted on the basis of unified theories. Okay, this is a kind of an awkward notation. So I want to improve the notation in 2 ways for further use. One is, I'll just, instead of writing down all these different components, it's like writing down the 3 components of a vector in ordinary space, or 9 components of a moment of inertia or something like that. It's better to use index notation. Certainly saves chalk and saves space in your mind if you just write something like this, where the Greek indices are the color indices, run from 1 to 3, and the Latin indices are the weak isospin that run from 1 to 2. So that would become this. This would become this one has no, so these have no Latin indices, these have no Greek indices. And these have no indices at all, so they're fine.
ER is -1 or -1, hybrid charge.
Come again?
The hybrid charge to the right-hand E, the left-hand is -1 or
-1. It's the average charge of the electron, which is -1. It's a good, the average is the same as, well, it's only one thing, so its average is the value. Okay. And now I want to make one more step, which is when we make fundamental couplings to the fermions based on the gauge principle, we do not change their helicity. They change, so left-handed particles only get connected to left-handed particles, and right-handed particles only get connected to right-handed particles. So if we're constructing a unified theory, we want to represent everything as just having one helicity. Really? Oh my gosh, all right. I'm really... So what we want to do is change everything to left-handed. We can represent the same entity because the right-handed field is also associated with that creates right-handed particles, can also be thought of as a field that annihilates antiparticles. It has a conjugate which just does the opposite. Either one of them can be used to represent those entities. So switching to left-handed guys by going to the antiparticles, we replace this by U, and now it's the antiparticle. We put a bar over it, we lower the index, and we change the sign. We no longer have to label right and left because everything is going to be left-handed. So this one goes to that, this one goes to and so on. So let me just now summarize and neaten everything up by writing down the 6 entities in the form so that they're easily digested and easily used for unification purposes as Q left equals, by definition, Q alpha A I'm sorry. I'm sorry. Just simply Q equals Q alpha A, 1/6. These are, if you have the notes, these are equations 11 through 15. U bar equals U bar beta minus 2/3. D bar equals D bar, so these are the shorthand notations, D bar gamma plus 1/3. L, which is already left-handed, is L D minus 1/2, and E bar is E bar of plus 1. And finally, N is the same as N, 0. So there are 6 independent entities. If we ask how many different degrees of freedom they represent, this one represents 6. Six Weil fermions, if you like. This one represents 3. This one represents 3. This one represents 2. And this represents 1. And this represents 1. So without n, we have 15. And with n, we have 16. And although, given the amount of phenomena that the standard model captures, it's really impressive that you can do so much with so few building blocks. Still, it's a lot of building blocks compared to one substance that we'd like to have. Okay. So if we're aiming for a unified theory, somehow we have to organize this structure into a multiplet under the larger group that reduces the number of independent components from 6 to a more reasonable number. Okay. And as you'll see, if we do SO10, we'll get down to 1. It requires the 16 version, 16 fermions or 6 entities. So it requires n, but does a beautiful job of organizing things. SU5 organizes it not quite as tightly, to 2 plus 1 more if you plus n if you include n. So the 2 include 15, and then there's n. Okay, so that's the promise of that unification will organize this and also explain and the funny hypercharges. So instead of being numbers chosen phenomenologically to match the observed electric charges of particles, they will be things that are theoretically determined. And so it really does improve the standard model a lot in this qualitative way. That's what I'll explain after the break. Yeah. So now we can take a question or two, right?
If you lower the symmetry from SO5 down to SO3 plus SO2 plus 1, does that mean
Then all these things are independent. Then you're
5 plus 1?
Then it's 5 plus 1. Right? 5 plus 1 entities. Right. So you have 15 plus 1 degrees of freedom. The standard model organizes it into 5 plus 1. SU3 organizes it into 2 plus 1. And SO10 organizes it into 1.
All those coupling constants have to be the same.
All the couplings are the same.
Yeah.
And so it's a pretty nice thing, and especially that's amplified by the fact that these funny numbers all get explained too. Okay, so that's what I'll show you after the break.
Okay. 10 minutes.